Students will often comment that all these properties, problems, examples, everything's just kind of mixing together, and it's hard. Yes, it's hard. If we were in the classroom, you'd feel like it was challenging. It's no easier that we're not together outside of the classroom. I want to encourage you, though, to keep trying, keep focusing, watch the videos, watch the extra videos. If it's your goal to learn this, I'm trying to give you ways. But again, you have to want this. And as I would have told you in class many times, it's ouch too. So yeah, things are getting a little harder. We're learning new ideas. The good news is that many of these ideas, they do go together and they start to overlap. You're going to find that to be true today. In fact, some of the things that we go over today, you would have already learned in Algebra 1. We're just adding an Algebra 2 twist to them. And so we're going to be taking a look at properties of rational exponents. Really, these are just properties of exponents. And some of these properties, again, we've been using this year. We're just going to kind of focus on a different version of the exponent. It's a rational exponent. Now, before we do that, let's do a problem that involves integer exponent. This would be like something that you should feel like we've done this year, that you did other years. And so how about something like this? 4x cubed, 2x squared. Now, it is a multiplication problem. So we've got some coefficients. So don't do anything different with those. It's, of course, 4 times 2. But we also have some exponents. We've got this x cubed and x squared. Well, as we've said and joked a couple times, this is the atom property. You add those exponents because now you have a total of x to the fifth. Now, what's happened in this problem is that we have had a product of powers. In other words, we've had a multiplication problem. And whenever you have a multiplication problem that has the same base, so the bases have to be the same. In this problem, that was like the x's were the same. Then you're going to add the exponents. You're going to add the exponents. And this is something that you've always done when the bases are the same. You add the exponents. So we have x to the fifth. Now, when you look at this problem, we want you to say that it's the same thing. The bases are the same. So when the bases are the same, we add the exponents. So the only question is, how do you add a half plus 3 halves? Well, a half plus 3 halves is a nice little fraction addition problem. Remember, you add the numerators and you keep the denominator the same. So we get 12 to the 4 halves, otherwise known as 12 squared. And, of course, that's 144. Now, if we were in class, some of you may have asked, well, why didn't you multiply the 12s? Why didn't you multiply the bases? Well, it didn't say, well, that's not what we did over here with these x's, right? We didn't multiply those x's. We just kept the base the same. So whatever the base is going to be the base of your answer. And if the base is x, then our base is x over here. If the base is 12, then the base is going to stay as 12. So the only thing we do is add the exponents. We keep the base the same. How about if we have a quotient? Okay, now a quotient is really a division problem. First off, we have some numbers that really don't involve exponents, and you can always divide 8 and 2. I hope that you would divide those today and still get 4. But really, the part that's kind of new here is, well, I don't want to say new, but the part that we're focusing on is the part that involves the variables. Now, when you have like an x squared over an x squared over an x, you would cancel those exponents. You would subtract those exponents. You always subtract the top exponent minus the bottom exponent, and in this case, that's going to leave you with just x to the first power. Now, because we started with more x in the numerator, we're going to put our answer in the numerator. So again, we have x to the first power. Now, we also have a y that we can subtract. In this case, when you subtract the y's, you end up with a y squared. But again, there's more y in the denominator, So that's why our y squared is going to go in the denominator. So do you see what happened here? We had the same bases. It's actually always the case. You have to have the same base. And we subtracted the exponents. So again, you always subtract when you have a fraction. And you want to put your answer wherever there was more to begin with. So let's try that with rational exponents. By the way, rational exponents, those are fraction exponents. So here we have fraction exponents that we want to subtract. But honestly, before we do that, make sure that you keep the base the same. So the base is still 125. A common mistake here is that kids want to try to cancel the base also. We don't cancel the base. We keep the base the same, but we subtract the exponents. Now, when you subtract the numerator minus the denominator, you get 1/3. So our exponent's going to be 1/3. That is 125 to the 1/3. Now, interesting moment here, 125 to the 1/3. You should realize that that is the same as a root of 125. Actually, the third root. So, is there a third root of 125? Well, yes, there is. There are 3 numbers that multiply to be 125. In fact, I can take out all of this 125 and replace it with a 5, because the third root of 125 is 5. Now, soon I want you to skip writing this step, and I want you to be able to just look at this 3 and say, hey, that's the third root of 125, and come up with the answer of 5. What if we have 2 exponents? What if we have like a power to a power? Now, I don't know if we've talked about this specifically this year, but there is something that you do with these exponents, and quite simply what you do with them is you multiply. So if I multiply these exponents, I get obviously -10. Now, negative exponents are bad. You don't want a negative exponent in your final answer. And there's this rule that says that if you have a negative exponent, you want to flip it over. Actually, what you're flipping over is you're flipping over the base. Right now, the base is x over 1. If we flip the base, we get 1 over x. So when I flip the base, I'm able to make my exponent become positive. And so my final answer here is 1 over x to the 10th. Again, we just don't want to have a negative exponent. Now, do you see what happened in this problem? We multiplied the exponents. You multiply the exponents whenever you have like a power to a power. Now, a power to a power is when you have 2 exponents side by side. So clearly there are 2 exponents side by side here. So we're going to multiply the exponents. Now, as we've done in every problem, you keep the base the same. So the real question here is, how do you multiply 2/3 times 3? Well, you might want to think of it as 2/3 times 3 over 1, so that you can then multiply the numerators. Of course, you get 6, and you can multiply the denominators. Well, it looks like 6 over 3 comes out to be 2, but really that's just the exponents. Now, in class, a common mistake is for students just to say that the answer is 2, but you want to make sure you realize that that's the exponent that we get. So, of course, 8 squared is 64, which would be our final answer. We're trying to do the same thing that we would have done if we were just dealing with regular integer exponents. And in a problem like this, we would have distributed, we would have applied the exponent to each term. Now, there's actually 3 terms here. There's a -2, so -2 is going to get a raised to the 3rd power. There's an x, that's going to get raised to the 3rd power. And look at this, we have a power to a power. We have 2 exponents. Remember what you do when you have 2 exponents? Well, in the case like this, you multiply them. So we get x to the 9th. Now, -2 to the 3rd power. -2 to the 3rd power. Be careful, that's not -6, but it's -2 times -2 times -2. Well, -2 times -2 times -2 is actually -8. Still have our x to the 3rd, and of course we got this y to the 9th. So what did we do? We distributed, we applied. I'll use the word distribute, although technically maybe a better word to say here is that we would apply, but to all. You apply to all. Okay, so can we do that with a rational exponent? Okay, well, yes, we can. You just have to apply the 1/2. You have to distribute the 1/2 to both of these. So I get 16 to the 1/2. I get 25 to the 1/2. Now, remember, if you have an exponent that's a fraction, the denominator is the root. So you can actually do the root of 16. You're actually doing the square root of 16. Well, that would be 4. You can also do the square root of 25. You can do the root of 25, and that would be 5. But look what we have here. We have now 4 times 5. Well, of course, that is equal to 20, which would be our best simplified answer. Okay, so I want you to change 16 to the 1/2. I want you to change that to 4, and 25 to the 1/2. Remember, that's the same as the square root of 25. I want you to change that to 5. If you have a fraction, it's no different. It's really just more distributing. You're just going to take the exponent and you're going to distribute it to all parts of this fraction. That's a lot of arrows right there, but if you take the square and you put it on -5, that's going to give you 25. Be careful, not -25, but 25. If you put this exponent on the x, you're going to multiply those powers. You're going to multiply, you get 6, and of course you put it on the y to get a y squared, and you put on the z to get a z squared. Now there's really nothing else that I can do with this problem because none of the bases are the same. So don't try to cancel the exponents. That would be silly. Those are not the same type of bases. Can we do this with a rational exponent? Yes, we can. You're going to take this entire exponent and you're going to apply it to both of these. So we get 16 to the 1/4, get 81 to the 1/4. Now remember, something like a 1/4 power is the same as a root. You don't really have to write this, but I just want to remind you this is the 4th root of 16. Now the 4th root of 16 is not like dividing by 4, but it's like finding 4 numbers that can give you 16. And oh, by the way, they have to be the same 4 numbers. So that's why it's 2. That's the 4th root of 16. What about this 1 right here that we seem to kind of be ignoring? What about this 1? Well, that would be the power. I have ignored it because a power of 1 is going to allow this to still equal 2. 81 to the 1/4 power. 81. You're trying to find 4 numbers that multiply to be 81. Now you can try this on a calculator. You can test some numbers. Eventually you'll arrive at the number 3. Okay, because 3 times 3 times 3 times 3, that is equal to 81. Okay, so our final answer here is 2/3. All right, so now's an opportunity for you to try 3 problems. Just like if we were in class, I encourage you to do anything that you think is right for all 3 of these, and I will be behind you then ready to go over it. But push pause, and when you start it back up, I will be explaining each of the problems. All right, so here's a good example of a product of powers. That's a fancy way to say that we're going to add the exponents. Now, adding the exponents is actually the only thing that you do. Make sure that you do not multiply the bases. Don't take 25 times 25. Instead, you want to keep the base the same. Now, when you add the exponents, you already have a common denominator. So all you got to do is add the numerator. That means you're going to get 5 over your common denominator of 5. Well, of course, when you simplify that, you get an exponent of 1. So 25 to the 1st power, well, you might as well just write that as 25. Now, when you have a fraction, you want to subtract the exponents. You should subtract the top minus the bottom. I say should because there are some other ways to approach this, but if you subtract top minus bottom, you discover that you get a -1 over that common denominator of 3. Now, the final answer is not -1/3. Rather, that's the exponent that will be on your base. By the way, don't cancel these bases. That's a common mistake. Instead, we keep the base the same. Now, how am I going to finish? What am I going to do about this 8 to the negative 1/3? Well, because there's a negative exponent, I have to have this thought that I'm going to flip the base. You see, the base is 8, or 8 over 1. If I flip that, I get 1 over 8. But the exponent becomes positive. So it's really now thinking about a positive 1/3. Careful, don't flip the exponent to be like 3 over 1, but only flip the base to be 1 over 8. But you do make the exponent positive, and now what I got to do is I got to think about 8 to the 1/3 power. Now remember, 1/3 is the same thing as the root, so that would be like finding the root of 8. Well, we've seen that many times. The third root of 8 is 2. So I end up with 1 over 2. All right, and this last one, it's a good example of a power of a power. In other words, 2 powers. What you're going to do is you're going to multiply those exponents. When you multiply the exponents, you get 2 times 5, which is 10. You get 3 times 2, which is 6. Now, 10 over 6, you might as well reduce that by 2's to be 5/3. But careful, your final answer is not 5/3, but 7 to the 5/3. Okay, because I still have to have that base. Now, can I do 5/3? Can I do the root of 7? Well, it turns out that I can't unless I'm using a calculator, because there's not 3 numbers that multiply to be 7. So what we do in a case like this is we just leave this alone. We just leave it as 7 to the 5/3. All right, well, when you're ready, we're going to flip the paper over to the back, and we're going to take a look at some problems that start to mix together the exponent ideas from today with the radical ideas from a few days before. Notice, too, that we want to write our answers in radical form. So let's see how we can kind of put a couple ideas together. You see, here we have 8 over x to the 1/3 power. Now, yes, you should and can bring in this exponent. You can distribute it, but there's some things you can already do. Like you can do 8 to the 1/3 power. 8 to the 1/3 power is like doing the root of 8. So that's going to right away turn into 2. But when I bring the 1/3 power on that x, maybe I should change that to radical form. I say maybe because we want to write the answer in radical form. And plus, this gives us an opportunity to think about how to get that radical out of the denominator, right? You're not allowed to have a radical in the denominator. So this is a good example of multiplying the top and bottom by some more denominator. How much more? Well, remember, you want to end up with a total of 3. So I'm going to have to multiply by 2 more. I'm going to have to multiply by an x squared. So we multiply top and bottom by the root of x squared. And let's see what this final answer is going to look like. I still have that 2 up there. This root of x squared, that's not really going to change in the numerator, but as we've said a few times in the denominator, that's going to leave us with a perfect amount of x to the third. In fact, so perfect that we're able to cancel these 3's, and it leaves us with just an x in the denominator. If you want to skip right to that, I certainly give you permission to do so. How about this lovely problem? Now, yes, there's a negative exponent, but before you get worried about it, you first have 2 exponents. You have a power to a power. Whenever you have 2 exponents, you're allowed to multiply them together. Remember, you're going to multiply. So how do you multiply 2 times negative 1/3? Well, I would suggest that you think of it as 2 over 1, so that you can multiply the numerators to still be negative 2, and you can multiply the denominators to be 3. Now, I still have this negative exponent, but at least it's just 1 exponent. And since it's negative, we're supposed to flip. What are you going to flip? You're going to flip the base. So now I end up with an x over 1. Okay, but really that's the same as just having x, because we normally don't write things over 1, and now the exponent becomes positive. So we have x to the positive 2/3. We basically flipped that up to the top. Now, nothing wrong with what we've done. In fact, that's what you were supposed to do. But since we want the answer to be written in radical form, then we take one more step and we put the power, the power as our exponent, and we put the denominator, we put that as the root. And so we end up being able to write the third root of x squared. Now, you've seen me write this on the outside before. Yes, you're allowed to write it on the outside. You could say the third root of x, that whole quantity squared. Either one of these would be fine. Everybody's favorite, a fraction. Okay, well, we can at least take care of the coefficients. The coefficients are going to divide. They're going to reduce. They're going to become 1/2. Okay, there's really nothing fancy there, nothing with the exponents. Now, we do have some exponents. You're supposed to subtract them. You're supposed to subtract the top minus the bottom. Now, when I subtract top minus bottom, I actually find myself having a double negative, which I highly suggest that you change to a positive. So really now I'm trying to add these fractions, but of course you can't add fractions unless you have a common denominator. So we do have to change to a common denominator. When you look at 4 and 3, you should be thinking that you can make both of those denominators become 12. If you multiply by 3, then you get a new fraction, 21/12. And if you multiply this one by 4, of course, that'll get you a denominator of 12, but since you multiply by 4, the numerator becomes 16. So 21/12 plus 16/12. Well, that's 37/12, and that is going to be our exponent. That's going to be our exponent, 37/12. Kind of strange, but what I want you to realize is that it's the exponent on x. Now, sometimes students aren't sure where to put x. You can see that I put it in the numerator. That's because what we've done is we've combined both of these to be just 1x. So I don't have an x in the denominator anymore. It wouldn't make sense to write that down there. Instead, I've combined this to be just 1x. Now, 37/12, again, is a strange exponent, but it does represent a radical. 12 is the root, 37 is the power, so I can write this as a radical. And what to do with this 1/2 that's been hanging out? Well, it's just in front of your radical. So you have 1/2 x, you have 1/2 the 12th root of x to the 37th power. Now, this last problem here, we got our crazy hat. It is a tough problem. I'm going to be honest. I'm going to show it to you. It is more of a bonus problem. I don't want it to frustrate you, but I do want to introduce to you, I want to show you that you can do a problem that involves a lot of variables. Even if it's the root, that's the variable. And so I'm going to essentially apply this root to the terms that are inside of here. Now, when you apply the root to the 3, that is the first one here. There's nothing you can do, so we would just call that the nth root of 3. When I apply the root to the 2n, I'm doing the roots, which means that you divide the n's. And when you divide the n's, they divide to be 1. So I end up with 2 to the first power, or just 2. But the important thing here is that it's not the root of 2 anymore. I was able to take that out. You've seen me often draw the arrow this way. It's still the same idea. It's like I took the 2n out. Now, I can also apply the power to the 2n, that is to the x to 2n. And again, I'm going to divide those n's. Well, when you divide them, you also just get them to cancel. So I end up with an x squared. Again, that x squared has actually come out because the root divided. Now, this n, or y to the n plus 3, this is a little tricky. You might say, well, can't you just, just apply, to both of these in some way? Not quite. What I first need to do is realize that if you're adding exponents together, that would have been the same thing as having a separate y to the n and a separate y to the 3. Now, what I just did right there was I reversed the atom property. And you reverse that property, you can actually split this up to be 2 y's. those are the two y's that are going to receive that root. And when they receive that root, once again, I'm going to divide. That's why the ends divide to become 1. And, it doesn't look like I'm going to be able to divide too much with the last one. So instead, I'm going to leave it in radical form. Now, I've got 3 items that have come out of the radical. Those 3 items are able to be written in front. And honestly, I have 2 items that are still in the radical, and so they remain here. Okay, again, tough problem, but we basically were able to take out the even ends. We took out the even ends, and we left behind the ones that didn't divide evenly. Okay, now try the homework. You're not going to see a problem quite as tricky as that, but try the homework, and then in the next video, I give an opportunity for you to listen to a select group of answers for this homework.